Thank you so much, Bill. It's an honor to present today to all of you. Thank you for attending this session. So what I want to really talk about is actually spurred a discussion and more like a thought process amongst you all distinguished data scientists is about the current state of affairs of machine learning models that we see deployed in production. So the main topic of my talk is going to be interpretable machine learning models. A little bit about myself. I have a background in econometrics. I did my PhD from the University of Maryland, primarily focused on environmental and health policy research kind of topics. Worked at the World Bank, worked at the health policy think tank as well, working on a lot of disease burden evaluation models, so today's scenario actually is very similar to what I was doing a couple of years ago when I was there, because that agency was the official agency for the federal governments to understand the disease burden impacts on the GDP. That said, I've also worked with a Kindle marketing research group before my current role, leading a team of data scientists at Expedia Group, building a conversation platform. What I'm going to also talk about is my whole journey, my observations that I've made over the course of my career thus far, which I've noticed, transitioning from an econometrics background to machine learning background. What are the advantages and the major gaps that we see today? With that, let's start out with what exactly is machine learning. As John Hennessy once said, machine learning is the hot new thing. But more formally, some of the godfathers of machine learning, as we call Alan Turing, for him, the definition of machine learning is a machine that can learn from experience. Arthur Samuel, machine learning is a field of study that gives computers the ability to learn without being programmed. And more formally, the definition that kind of gets followed in current scenarios is what Avron Barr and Edward Feinbaum defined in 1981. It's an information processing system that can ask questions. Basically a system just like the human brain, all by itself. So ML is technically a computer program that we train to learn from experience, which is historical data, with respect to some class of tasks that we define and a performance measure again defined. And if its performance and tasks as measured by P, as we call the performance measure, improves with experience, it is known as a machine learning process. There's a lot of applications of machine learning today in the industry. This is some of the examples, although you can go on and on as to how machine learning models are utilized today. Self-driving car technologies, recommendation engines, the news feeds, search engines, the finance sector, determining, debt repayment candidates, virtual assistants or chatbots, which is actually my current focus as well. Stock market, algorithmic trading, disease predictor models, facial recognition technology, and even an algorithm for journalists to predict captions and the sentiment around captions. So that said, what really lacks today, as you see, is like in all of these use case scenarios, some of the things that we would like to understand deeper is situations like when an automated system determines whether a person is a criminal or not, when a language translator attaches a specific gender to professions, if demand is predicted to go down, or you give treatment advice for patients with similar disease and give them different treatment recommendations, we really want to understand what factors are driving these outcomes and why and how they're interacting with various other factors. And the deeper question out there is also, when a model, a machine learning model, selects features, why did it not select some of the other features? And what would happen if they did select certain other scenarios? And are they truly reliable? So majority of the machine learning based solutions in the industry today are built using black box models. Now, this is a typical representation of a black box model. There's a bunch of algorithms that fall into this category, mainly ensemble models, which combine multiple layers of the models together and do a bunch of magic inside and then give us an output or outcome as desired. Some of the popular black box algorithms that we see today, it started with random forest. There was a time when the industry was using random forest for every scenario. Moved on to gradient boosted trees, especially after the AlphaGo success. We went to deep neural networks and subsequently to deep convolutional neural networks and hidden Markov models. All of these solutions, though, are black box algorithms. But why are black box algorithms so popular? And one main reason why black box models were mostly deployed in the industry was their accuracy in the training data set. Now, as more and more of these models started getting deployed into production, we also started seeing a lot of scenarios which you didn't see in the training data sets. Say, for example, this is an example of an algorithmic trading where it probably picked up the word O'Reilly, and as a driver, and it's a, as a driver, a predictor, key predictor for the stock for the company O'Reilly Automotive. And when Bill O'Reilly hit the headlines, the stock also started doing extremely well. Now, another example is when you see a certain passage, these models being utilized for NLP, NLU purposes. Say for this example, where you train the machine to read the paragraph and then understand the meaning, and then you ask a question to the machine to figure out whether or not the machine understood things correctly. Now, in this particular example, the machine does give the right prediction. But at the same time, if you introduced another sentence right afterwards, the prediction starts changing. So what really impacted the original prediction to get changed when a simple sentence was introduced? Okay, we can also look at some more failures of ML models where you introduce some perturbations in these black box models and you see scenarios that are totally different from the expected behavior. So as you know, a human would look at both pictures and say this is a pig, but if you introduce a very tiny noise, even a 1 pixel, and this one is like even tinier than that, you see that the model starts predicting this picture as something totally different. It's an airliner. In this scenario as well, it was a panda picture, you introduce some noise, and it's very, very sure the same exact model, but now it's a given. Again, some more examples where for a human, the left-hand side is all gibberish. And you have these directly encoded and indirectly coded images, but the state-of-the-art DNNs trained on the ImageNet will start believing that these images are actually some objects. And so as a result, there are now, like in the last couple of years, dozens and dozens of research studies that are demonstrating the impact of these adversarial attacks. Now, as we start deploying the models the way we thought were working very accurately on our training data, we also start seeing a lot of mainstream technology products failing. And some of the examples would be, I think IBM had a recommender system that was bought by a couple of hospitals, but it turned out that it gave actually dangerously incorrect cancer treatment advice. Chatbots that were easily corrupted by trolls. Face IDs are defeated by 3D masks. And there's a bunch of all these use cases that every so often that you can find that are failing. And as Pedro Domingos, the author of Master Algorithm, says, we still need to think deeper into the kinds of algorithms that we're using. And what we find is more and more people going by some of those niche crazes and trying to train and build every use case scenario based on those. But it turns out that in reality, because these models were just fitting towards accuracy, we did not understand what they were truly doing, and they probably were not the best way to build these use case scenarios. So interpretability is something that black box solutions currently, it's very hard to get out of those. And unlike traditional statistical models, these solutions, there is often a big gap in trying to understand what are the features that are deployed or employed by these models, how exactly did they interact with each other, why did they do a certain, combine the inputs in a certain way and by not another way, and are they truly fair and are they truly trustworthy? So couple of big reasons why the industry needs to focus on interpretability. Biggest reason is in a lot of situations, especially in regulated industries, ethics and bias and fairness and trust needs to be ensured. So we do need to ensure that predictions do not discriminate against certain groups. Actionability. Ensuring only truly causal relationships are selected. That is, when you are building a model where you're predicting a particular person's churn and you have a very high probability, have very high accuracy in the probability of this customer's churn rate, without truly knowing what the causal relationship were towards a churn process, there is nothing much you can do beyond knowing who is going to churn. And so it's really important for us to be able to decipher into how these models were doing the predictions in the first place. Stability. When you deploy models, everybody who's worked with in data science and knows that when you deploy something, the scenario can change totally from your training scenario. So to ensure that small changes in the inputs do not lead to large changes in predictions, one needs to understand, again, the model composition as to how much each factor contributed. And also in regulated industries, especially to ensure that the sensitive information is being protected, we are careful about the privacy. So formally, if we were to define interpretability, there's a couple of things one needs to understand. One of the things is obviously to understand the complexity of the relationships within each features that went into the model prediction. Whether it's linear, nonlinear, monotonic, non-monotonic, to be able to visualize these relationships, we need to understand whether interpretability is a global interpretability or a local. And I'm going to go into the details when I go into some of the current methodologies regarding those. We also need to have trust in the model, and in order to ensure transparency in our decision-making process. And we need to make sure that an interpretable modeling technique for that we come up with for black box models are model agnostic, or whether they're model specific. Say, for example, if you look at this image, this one was, so there's a classification, image classification made by Google's Inception network. And the top 3 classes predicted were electric guitar, acoustic guitar, and Labrador. If you wanted to determine what features that are correlated and what are the ones that are causing this outcome, we could probably improve the classification accuracy. Another reason, another big reason for us to have interpretable models is to be able to prevent unintentional unfairness. Say for this example, these are Snapchat filters, which unfortunately is unintentionally promoting harmful stereotypes, not by design, although the algorithm is by design. And so one needs to, again, make sure that these kinds of scenarios are avoided. This is another example. I validated yesterday again, and I've seen this happen for a while. This is Google Translate. And when you go to Google Translate and you're trying to translate from one language to another, you start seeing patterns related to professions. So when somebody writes in Malay, which is the Malaysian language, the same exact thing about someone is a doctor, the English translation becomes he is a doctor, but when it's the case of a nurse, it becomes she is a nurse. Same thing with professor and secretary. It assigns gender-specific stereotypes, although you can see in the original language is gender agnostic. Okay, so why are we facing some of these issues? In a typical classical modeling technique, there is a defined structure. So when you have a linear regression model, you're fitting it. You essentially, so the blue line out here, you're essentially fitting a line which is y equal to beta x, right? X is a vector of factors. You know exactly the contribution of each factors as you fit the line, and you know which features are part of the model, and you know how they interacted. In a logistic regression model, again, There's a relationship with the probability of being in a particular class, which is a linear function of the exponentially attributed, again, of the features. So you're able to get the odds ratio and the marginal impact of each features. You're able to derive it. Support vector machine, again, you're able to, and this one is a linear example, but you could have different ones as well. You're able to see how distinctly, or what the factors are that define the plane that distinguishes between the classes. Decision tree, probability tree, again, we are able to pinpoint and see how the outcomes are split, the contribution of each factor, the importance of each factor, and so we do have a good understanding of how the decisions were assigned. But the reason why the industry moved away more and more towards the black box models with more to do with accuracy. So a lot of data that we see today, the real life data with tons of features, were easier fitted with neural nets and deep nets and convolution neural networks than your classical regression techniques, and which were more interpretable. And being, working in the industry, one of the key things that one is chasing towards typically has been only predictive accuracy. So why is it so different in a black box model structure? So as all these images will show, they are typically ensemble techniques. Honestly, by design, you should, the algorithm is actually fitting different layers of simpler models and then combining them using some weightage or process together. But that process is unknown and it's undecipherable in most of these mainstream state-of-the-art modeling algorithms or techniques that's utilized. And that leads us to the conundrum, or when we see a lot of ill-fitting machine learning models in the production and the outcomes thereof. So when we talk about interpretability, there is a couple of things that matter when we build an interpretable technique. Now, one of the key things is the scope of the interpretability, whether something is globally interpretable, or are we going to build a technique that's locally interpretable. Globally is something that you would directly train from the data, but with interpretability constraints, and you would mimic the learning based on that. Whereas local is model making specific predictions for a particular group. Now, your classical learning models are typically globally interpretable models. So you know the contribution for each of the factors or features, predictors towards the outcome. Evaluation of interpretability techniques are equally important. So one is scope and the other one is evaluation. The evaluation focuses more towards explainability, because you want to understand, you want to know, yes, what are the factors, but you also want to be able to understand the causality behind it. So it relates to the counterfactuals and how accurate those explanations are. And again, the interpretability techniques, one of the key factors, again, that matters is how accurate are these interpretable techniques, especially if they are built on locally interpretable scope. So one of the most commonly used techniques currently to decipher black box models is known as LIME. So LIME is local interpretable model agnostic explanation. Now, it's a technique that localizes a problem regardless of the model structure. So you could be fitting a deep neural net, but you're only evaluating the interpretable portion and trying to figure out the features and feature importance for a particular localized sample. It uses then a surrogate model trained on perturbations on the data points being investigated for explanations. The local predictions are explained by simple interpretable models. Most people use linear models, although you could use some more other techniques as well. It doesn't generate explanation for the whole model. But it does help you with explanations of predictions of the black box models. It's like something better than nothing scenario. There is an interpretability versus fidelity trade-off, in which I guess the next diagram will show us. So what essentially this process does is, after you would fit a model, you would take a data sample and you create perturbations in the feature values. And the data sample that you would take is based on certain localized constraints that you are interested in. Then you would put in some noise to some of the features to create some perturbations. And you would then base your evaluation, or you would actually need to set up another model now on this subset of the data that you created as a sample. And you would now reevaluate this using simpler methodologies, which are the classical interpretable models, like a linear regression with regularization or decision tree, etc. The output then comes out as a list of explanations with contributions of each feature for predictions in the sample, and that's your locally interpretable model. But there are major drawbacks to the LIME, which is in the industry right now a very popular technique to reverse engineer some of the black box algorithms. One of the major drawbacks is mostly linear models are utilized to approximate local behavior. So if, for instance, even within the localized area, there was a non-linear relationship, you would not accurately then be able to estimate the impacts. Types of modifications are very use case specific, as you would draw out your sample from, and often simple perturbations are not enough for delivering robust agnostic explanations. Although if you start manually controlling these perturbations, then you run the risk of introducing bias. There is another popular technique that is utilized. So there's like 5 or 6 ways that people utilize right now to de-decipher or reverse engineer black box interpretations. These are the 2 most popular ones, LIME being the most popular one because of ease of use and ease of computation as well. The SHaP, or the Shapley Additive explanations, is another methodology that was introduced a couple of years ago. It's based on the game theory, optimal Shapley values. So Shapley values are of average marginal contribution of a feature across all coalitions. So what you essentially do is you learn about individual features by studying them in isolation. So as you can see in this picture, is like you have these 2 scenarios and you have the prediction by your original model, and you try to decipher the attribution based on samples that you draw off, where these some of the features are turned off. So you basically decompose the final prediction into the contribution of each attribute um, based on an additive contribution. And so on the left at the bottom, you can see um, the model that decomposes the Shapley value. So that's the algorithm that is utilized to do that. And the way you do it is, as you can see on the top, is you build feature values by creating, again, similar to the line, perturbations in some of the features, and then study the impact of what happens when their perturbations are created. Now, there's a couple of ways. Shapley is more flexible than Lime, as in Lime is largely utilized using linear methodologies, which, as you can imagine, isn't a very probable use case in a lot of real life scenarios. Shapley is more flexible in that you can also utilize beyond the simpler methodologies, you can also utilize the black box methods within this to learn the models. Okay. So Shapley and Lime were being utilized a lot, in the recent literature by a lot of researchers who utilized it for different use cases and demonstrated value from those use cases. But a recent paper by a team of research scientists at Harvard, Slack et al., in December actually demonstrates that even Lime and SHaP may not be that reliable. So what these people did was like they used two different data sets, but they started off with a COMPASS data set, which is the Correctional Offender Management Profiling data set. And they ran some experiments using Lime and Shapley. And what they find is that as they ran these experiments, they realized, as you can see from these diagrams here, that they're able to create these adversarial attacks and where the feature importance completely changes. And what this really means is that even Lime and SHape, given the way these techniques are designed, are not robust and reliable to adversarial attacks. And that essentially means that, because these were localized ways of interpreting the models, they were not reliable to begin with because, either the samples or the way you take the samples or the way the whole technique is built, it isn't a reliable way of understanding the features if someone's trying to interpret features out of that. And that brings us to kind of like square one again, is we still face the issues that we face, as in we do get a lot of accuracy. We have a lot of models deployed in production today that that have proven to be, having adverse outcomes, unintentional. And we do need to understand in a better way, how some of these relationships are occurring. So, so one of the things that one really needs to start looking more into is, more causal techniques, trying to ensure that counterfactuals, causal reasoning is employed before deploying some of these AI applications. Although causal reasoning methodologies are largely still you know, more correlated with non-black box kind of techniques, the classical methodologies. So there's a trade-off there. We keep touting in the industry as we increased accuracy, you know, one step at a time, some company or some research comes and says, hey, I used this algorithm and I got, this much accuracy. And what you start seeing is like everybody starts using that algorithm to try to solve for every use case. And in my personal opinion, that is where we start failing. Yes, there are ensemble techniques where people are combining different algorithms, but essentially, again, most of them are still falling into the same methodological trap, which, any ensemble models right now are facing. And so my message here is for everyone to start exploring more techniques which would be, less dependent and more explainable. One of the things that I didn't go into the details here in interpretable models, and which is very critical again is in interpretable models, is the explainability part as well. So that said, that was in a nutshell what I wanted to really convey. Any questions?
Okay, great. So we have a few more minutes. If you have questions, you can either in the Q&A sessions or you can type in the chat window. I think there's a question in the Q&A. Can you see that?
Yeah. So the question is, can you please share something on time series models and interpretability? So traditional time series models are interpretable, right? Like any classical learning models. I think what you are referring here is more towards the time series network-based models. And interpretability, again, it's a common thing, issue that each of these techniques have a gap in right now. There are a class of time series models which are which go beyond just utilizing the lags, as we call it, the time component alone of the series that they're trying to predict. And those are the cross-sectional data where you can actually add in other features. And those typically, at least in econometrics, there's a rich literature out there. Traditionally, those have been pretty robust. And so that would be something that, that should be utilized, in my opinion. I mean, I have utilized a lot of, like, most of my time series work has been utilizing factors beyond the series itself, where although the features can have their time series too, but you would go beyond your regular just the time series per se. And so I would highly encourage you to explore those methodologies and see if those fit your needs. There's another question here. Any tools or techniques to use to facilitate such analysis? Are you referring this in particularly about time series models, or in general about some of these interpretable techniques? So Lime and SHaP, the packages are available both in Python and R. About time series, if you're I am not so sure on the black box time series models, how well those fit, and I would honestly see that to be a bit of a problem, a challenge there, especially because the way these interpretable modeling techniques, the traditional ones, the way they're set up to be able to help in a typical time series, neural net kind of interpretation, because it's going to be hard for you to build a specific use case to do a local interpretation. So how do you suggest finding such factors beyond time series data, like you said? Can you add a bit on feature engineering of time series so such models are easier to interpret? Absolutely. But those are non-black box based approaches. They are panel data, cross-sectional time series data approaches that you have. There's a bunch of diagnostics you can perform to do your feature engineering process. But again, it's one of those traditional heavy manual effort kind of like, so it's not one of those auto ML kind of approaches. It is your traditional approach using cross-sectional data. There is a bunch of diagnostic tests that you can utilize to do the feature engineering for sure, and those are definitely easier to interpret. And you would, the way you would do classical modeling, statistical modeling, you would use the same, so they have their scoring for purposes of model determination. Then again, the counterfactuals, you're able to test on those and understand the the impact, the marginal impact of the features, and you're able to build interactions, which is a big gap in black box algorithms, is you are not able to understand interactions between terms, and which is again like even feature importances. When we try to interpret, we are not able, we get individual feature importances, but we are not able to understand if there is an interactive set of features where, so the impact of interactive features. Oh, thank you.
I think we have another question in the chat. Can you see that one? The last one.
Well, the last one says thank you.
No, in the chat. It's not in the.
Oh, okay. Sorry, I was in the Q&A chat. Let me go to the chat. Oh, okay. Well, in the chat there's, okay. Okay. So how do you think it's possible to identify those adversarial unintended consequences? Is it possible without interpretation? That's a great question as well. So people are, well, right now, I would say there is no foolproof method. All these interpretation techniques, Lime or Shapley, because they're contingent on the local use cases, people are trying to understand within the specific use cases. So definitely one way to start off would be to study the use cases which are more sensitive. Um, and so you can avoid unintended consequences. But again, the very definition, well, it's not the definition, it's like black boxes are black boxes, because we didn't set up, it's computationally way more expensive to understand the hidden layers as we see them, right? And so if there was a way, if computational, if there were advances in computation, we should definitely be able to decipher the exact pattern that the algorithm took, and maybe get a better insight of the whole process per se. Currently, there is not. And it remains like research in progress. There's a lot of research currently focused precisely on these aspects, and that's why we still say we are not in a generalist AI space yet. um, so there is some recent research on like improving accuracy using encapsulated encoders, um, that is there. But again, those are focused more on, so they're very different from convolutional neural networks, right? And convolutional neural networks, you're essentially creating a uniform universe of training, like, okay, every small use case, keep training, keep training, keep training, all of those networks. Whereas if you think about artificial intelligence as an equivalent of human intelligence, we do not take, we may have like millions and millions of neurons, and we may have vertices within our brain, but we do not need so many training use cases to train. We can figure out, we have something called intuition, and we are able to figure out, using our intuition and perception with very small number of use cases. So there are some models that people are researching on, some frameworks, but I think some of these things, unless we are, again, most of this research, when somebody is building these use cases, there's a theoretical aspect, and then when they start testing it, it's very specific to the data that they are testing on. And that's what I think has led to some of these failures that we saw. So in order for a ubiquitous kind of an algorithm, it still remains to be seen. But my suggestion would be, in any specific scenario, especially if you're working for regulated industries, deploying something there, to be able to make sure that you are able to identify, what your model or how your model is working in those particular scenarios. Adversarial, there are ways, by the way, of generating these adversarial, scenarios. And that is how one is actually able to research on all of these algorithms and its failures. Any other question? I think I got one here. How do you think it's possible to identify those cases when things went wrong in production running neural nets? That's a great question, and I think there isn't a foolproof way to really identify. I mean, in some cases, yes, right? Like depending on the situation, you would get to know that somebody got an adverse consequence and they pointed it out to you. So whoever got impacted of the outcome. In some scenarios, I know there was this example from a couple of years ago when that company found out they stopped doing it. So they had trained based on the resumes they had on file to automatically identify a successful candidate for their workplace. But what ended up happening was, like, traditionally in technology, you had men in the industry. So most of the resumes were those of men, and the model had picked up, the algorithm they were utilizing had picked up specific cues which were only gender specific. And so utilizing that algorithm, the company was actually losing a lot of qualified women candidates. And so that only got discovered later as a pattern. Maybe somebody saw it, but yes, it was human monitoring. You're right now there is no foolproof method. Like Julia Pearl, who's one of the godfathers of AI, who's the father of causality theories. According to him, we are way still very far from building generalist AI. The generalist AI would be something very similar to a human brain as we want, right? Something that would not require so much training examples. And training examples, like, I know recently I read, like, some top technology company, utilized like some trillion use cases and got a very high level of accuracy. Computationally, if you think of it, the resources utilized for such use cases, and again, I'm sure it's not going to be ubiquitously applicable for every scenario, maybe for the specific use case. It's, if you think of in terms of resources that gets utilized for running those kinds of complex models, we are spending a lot of resources. If we could identify much simpler methodologies, maybe sometimes, erring on the side of accuracy. So if I have a model that is 91% accurate in black box and the other one is 87%, maybe sometimes we may want to err on the side of accuracy, because we gain a lot more on the explainability and the interpretability. So, to your question, it's a great question. It's an ongoing debate, but I have not seen any research to date that, I mean, if somebody did that, it would be the hottest thing right now. But yeah, so it's like everybody needs to contribute, I believe. All of us in this field can contribute meaningfully in this exercise, as we think about our day-to-day work and how we are building things. What is a good place to start learning more about these topics? Not just with theory, but practical examples or videos or tutorials. So lime and shape, if you wanted to utilize, now depends really on what you truly want to do. Like modeling, it's like, it's a use case scenario that you're trying to build. What are the things that you need to impact? In some cases, you just care about the accuracy. You don't really care about the explainability. You are able to, there's a bunch of tutorials online. Coursera is a great place to start. But there's a bunch of tutorials online that get you started well. As well, on the programming aspect, I mean, the codes and syntaxes are easily available. I think what you're asking is more about the lime and shape, the interpretable part of this modeling process, correct? Okay. Oh, mainly in the interpretability area, not lime and shapely. This is actually, so what has happened is, it's only in the last couple of years that I see more and more researchers, given the failures that we started seeing. I would say like 7 or 8 years ago, right? All of this big frenzy about data science started. And if you looked at job interview, descriptions for data scientists, people would write, do you know how to do random forests? With the assumption in the industry that random forests could solve all problems. Then, Google came up with AlphaGo success, which was based on gradient boosted techniques. And so everybody would run after that methodology. Then, so on and so forth. It was like the neural nets, deep neural nets, convolutional neural nets. There's a, so that frenzy continued till there's a lot of models that got deployed in production. And as more and more failure cases in the industry started rising, we suddenly now see a lot of researchers going back and focusing on trying to understand what went wrong. And interpretability area, so it's relatively a newer focus, although if you think about it, it comes, causality, interpretability, all comes from Socrates. As early as Socrates started theorizing these things. So there's a bunch of theory you would find, but in the application part, econometrics is actually has always built on causality because it's focused on human nature, human behavior. And so you do need to understand causality. And there's a lot of borrowing in econometric literature and game theoretic literature about human behavior. So that might be one area you might want to focus on. Do you think deep learning algorithms are more powerful than traditional machine learning algorithms? Depends again on what you want to do. So if for your specific data and use case, there is no one size fits all, I would say. So neither or both can be very good in specific use case scenarios. And I think there's a website here you're pointing out, calling bullshit.org. Okay, so going back to the what I was saying. So deep learning vis-a-vis traditional machine learning algorithms, again, depends on your specific use case scenario. So, you would have to weigh it. And like I said, like say for time series, there was a question earlier. For time series, you could introduce other features as well. And they fall into the traditional machine learning side of things, econometric side of things, and see maybe you might get better explainability and interpretability, and maybe even be able to manually shape your accuracy. So I've had a lot of like success cases on that side as well. So it all depends on the use case you're trying to do. Hierarchical methods of learning or training, and also giving results in that form. All of the results today are very flat. Linear, scalar, and sequential. I hope my ideas are clear to you. Yes, I do agree with you because, again, a lot of these things are primarily because of computational efficiency. We can't, like you'll see a lot of deep learning methods, but most people will be utilizing, very, very simple algorithms within the deep learning structure. So the framework will be more, the hierarchical categorical, your framework will be complicated, but yes, most people do tend to use simpler methodologies. So it's also balancing your computational aspect of things as well, especially when you're putting models in production. That is a key concern. If you're working for one of those large resource rich companies, technology companies, then